Welcome! In this session, we'll explore LeetCode problem number 1727, largest submatrix with rearrangements. This is an exciting problem that challenges your understanding of matrix manipulation and optimization techniques. Let's dive in and uncover the best approach to solve it. In this problem, you are given a binary matrix, which is essentially a 2D array where each element is either a 0 or a 1. The task is to rearrange the columns of the matrix in any order you like, and then determine the area of the largest submatrix that contains only ones. Here, the area of a submatrix is defined as the number of cells within it. For the input format, the matrix is represented as a list of lists of integers, and the output is a single integer that corresponds to the area of the largest submatrix of ones after rearranging the columns. Let's look at the first example. The input matrix is a 3x3 binary matrix, 0, 0, 1, 1, 1, 1, 1, 0, 1. After rearranging the columns, we can transform the matrix into a new configuration, 0, 1, 0, 1, 1, 1, 1, 1, 0. In this new arrangement, the largest submatrix containing only ones is a 2x2 block, 1, 1, 1, 1. This submatrix has an area of 4 since it contains 4 cells. Therefore, the output for this example is 4. Now consider a second example. The input matrix here is a 3x4 binary matrix, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0. After rearranging the columns, we can create the following configuration, 0, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 0. From this rearranged matrix, we find that the largest submatrix containing only ones is a 2x3 block, 1, 1, 1, 1, 1, 1. This submatrix has an area of 6, as it consists of 6 cells. Therefore, the output for this example is 6. Next, let's look at another example to solidify the concept. In the third example, the input matrix is a 2x3 binary matrix, 1, 1, 0, 1, 1, 0. After rearranging the columns, the matrix remains the same, 1, 1, 0, 1, 1, 0. The largest submatrix of ones here is a 2x2 block, 1, 1, 1, 1. This submatrix has an area of 4, so the output for this example is 4. Finally, let's review some constraints and edge cases to consider when solving this problem. When it comes to edge cases, if all the elements in the matrix are 0, the output will always be 0 because no submatrix of ones exists. On the other hand, if every element in the matrix is 1, the output will equal the total number of elements in the matrix, since the entire matrix forms the largest submatrix of ones. For matrices with only one row or one column, the problem simplifies to finding the largest contiguous sequence of ones after rearranging the columns. These considerations are important for ensuring your solution handles all possible scenarios effectively. When tackling the problem of finding the largest submatrix with rearrangements, the ultimate goal is to maximize the area of a submatrix consisting entirely of 1s after rearranging the columns. Initially, we might consider a brute force approach. This involves generating all possible permutations of the columns, which grow factorially with the number of columns. For each permutation, we would calculate the largest submatrix of 1s using a histogram-based technique. While this method guarantees correctness, it comes with a significant drawback. The factorial growth in permutations makes it computationally infeasible for larger matrices. Specifically, the overall complexity ends up being O(n)(m)(n), which is impractical for even moderately sized inputs. This inefficiency prompts the need for a more scalable solution. To address the limitations of brute force, we can adopt an optimized approach using a histogram-based method with sorting. The key insight here is that explicit column rearrangements aren't necessary. Instead, we can simulate optimal arrangements by sorting histogram heights for each row. Here's how it works. First, we treat the number of consecutive 1s in each column as the height of a histogram bar. Rearranging these columns to maximize the area is mathematically equivalent to sorting the heights in descending order. Once sorted, the maximum area for any row can be found by multiplying the height of each column by its position in the sorted order, which represents the width. To implement this, we calculate the histogram heights for each cell, sort the heights row-wise, and compute the area for each sorted height. The time complexity of this approach is far more manageable, with O(m*n) for building the histogram and O(m*n) log n for sorting all rows, resulting in a total complexity of O(m*n) log n. This optimized histogram-based approach strikes an excellent balance between simplicity and efficiency. It avoids the factorial growth of brute force while still considering all possible column rearrangements implicitly through the sorting process. The elegance of this method lies in recognizing that sorting histogram heights allows us to simulate these rearrangements without actually generating permutations. This saves both time and computational resources. In terms of trade-offs, brute force guarantees correctness but is prohibitively slow for large inputs, while the optimized approach achieves the same result with a scalable O(m*n) log n complexity. Additionally, both methods require O(m*n) space to store histogram heights. Ultimately, this optimized strategy is the clear choice, as it provides a practical and efficient solution to the problem without compromising accuracy. This problem challenges us to find the largest possible area of a submatrix containing only ones, but with an interesting twist, we are allowed to rearrange the columns of the binary matrix independently for each row. To tackle this, we start by understanding the structure of the input matrix, which is mxn in size, with m rows and n columns. Our ultimate goal is to maximize the area of a submatrix of ones after potentially rearranging the columns. The first step in our algorithm is to pre-process the matrix by calculating a heights array. This array essentially represents, for each column, the number of consecutive ones ending at the current row. To compute it, we iterate through each cell in the matrix. If the cell contains a 1, we increment the corresponding value in heights. If it contains a 0, we reset that height to 0. This forms a histogram-like representation of the binary matrix, which sets the stage for further calculations. Once we have the heights array for each row, the next step is to rearrange the columns optimally to maximize the potential area of submatrices. We achieve this by sorting the heights array for each row in descending order. This grouping of taller bars together allows us to calculate the largest submatrix area efficiently. After sorting the array for a row, we compute the maximum submatrix area ending at that row. For each bar in the sorted heights array, we calculate the area of a rectangle where the height is the value of the bar, and the width is determined by the bar's position in the sorted array. Specifically, the width is equal to the index plus 1, since array indexing starts at 0. By multiplying the height with the widths for each bar, we obtain potential areas, and we keep track of the largest one. After processing all rows, the overall largest area found across all rows is our final result. This approach leverages sorting to maximize submatrix dimensions efficiently. The algorithm is built on a few key insights. First, sorting the heights in descending order is critical because it rearranges the columns to group taller rectangles together, which directly contributes to maximizing the submatrix area for each row. Additionally, a heights array can be viewed as a histogram, where the tallest bars grouped together yield the largest rectangular area. Another important factor is the efficiency of this approach. By pre-computing the heights array, we avoid the need for nested loops over rows and columns, reducing the overall complexity. In terms of data structures, the algorithm primarily relies on the heights array, which is a one-dimensional array that stores the height of consecutive ones for each column. For each row, a temporary sorted version of this array is used to calculate areas. The time complexity of this solution is driven by three main operations: computing the heights array in O(m*n), sorting the heights for each row in O(m*n) log n, and calculating the maximum area in O(m*n). Overall, the time complexity is O(m*n) log n, while the space complexity is O(n) for the heights array. To tie everything together, let's walk through an example with the input matrix 0, 1, 1, 1, 1, 1, 1, 0, 1. First, we compute the heights array row by row. For the first row, the heights are 0, 1, 1. For the second row, they update to 1, 2, 2, based on consecutive ones. For the third row, the heights are 2, 0, 3. Next, we sort the heights for each row in descending order. After sorting, the first row becomes 1, 1, 0, the second row becomes 2, 2, 1, and the third row becomes 3, 2, 0. Then, we calculate the maximum area for each row. For the first row, the maximum area is 2. For the second row, the maximum area is 4, and for the third row, it is also 4. Finally, the global maximum area across all rows is determined to be 4. This means the largest submatrix area, after rearranging columns optimally, is 4. This solution computes the maximum area of a submatrix with rearranged columns in a binary matrix. First, we pre-compute the heights matrix, where each entry represents the number of consecutive ones up to that cell in the current column. This pre-processing step involves iterating through each cell and updating the height based on the value immediately above it. Next, for each row in this heights matrix, we calculate the maximum possible area of a submatrix by sorting the heights in descending order. Sorting ensures that taller columns are considered first, maximizing the base of potential submatrices. For every column index in the sorted row, we compute the area by multiplying the height by the width, C plus 1, where C is the current column index in the sorted order. The maximum area encountered during this iteration is updated and returned at the end. This approach effectively leverages sorting to maximize the submatrix area, and the overall complexity is O, rows ** calls * log, calls, where the sorting step dominates. The code handles edge cases like single row or single column matrices seamlessly, ensuring robustness for all inputs. Here we start by importing the necessary packages and defining our solution class. The main method we are implementing is largest submatrix, which takes a binary matrix as input and calculates the largest possible submatrix area after rearranging the columns. First, we determine the dimensions of the matrix and initialize an auxiliary heights array to store the height of consecutive ones in each column. The algorithm begins by pre-computing these heights. For each column, we iterate over the rows and check if the current cell contains a 1. If it does, we calculate its height as 1 plus the height of the cell directly above it. This provides us with a way to measure the vertical extent of ones for each cell in the matrix. After initializing these heights, we move on to calculate the maximum area of submatrices. Next, we evaluate the maximum area row by row. For each row, we take a copy of the corresponding heights and sort it in ascending order. Sorting enables us to easily compute the width of potential submatrices by considering columns from right to left. For each column in the sorted array, the height is fixed, and the width is determined by the number of columns remaining to the right, which is simply the total number of columns minus the current index. We then calculate the area for the submatrix formed by this height and width, updating the max area variable if the calculated area is larger. Finally, after processing all rows, we return the max area, which represents the size of the largest submatrix that can be formed with column rearrangements. To solve the problem, we start by pre-computing the heights of consecutive ones in each column. In this example, the input matrix is a simple 2 by 3 grid. For column 0, the first row has a 0, so the height is 0, and the second row has a 1, so the height increases to 1. For columns 1 and 2, the first row has 1s, so their heights are 1, and the second row also has 1s, increasing their heights to 2. This gives us the resulting heights matrix, where each entry represents the height of consecutive ones in that column up to that row. Understanding this step is crucial because these heights will help us calculate the maximum area in the next step. Now we calculate the maximum area for each row based on the pre-computed heights. For row 0, we sort its heights in descending order, giving us 1, 1, 0. Using this order, we calculate the area for each column. For column 0, the height is 1, and its area is the height multiplied by the number of columns considered so far, which is 1 times open parenthesis 0 plus 1 close parenthesis is equal to 1. For column 1, the area is 1 times open parenthesis 1 plus 1 close parenthesis is equal to 2, and for column 2, the area is 0. The maximum area for row 0 is thus 2. For row 1, the sorted heights are 2, 2, 1. Calculating the area for each column, we get 2, 4, and 3 respectively, with the maximum area for this row being 4. Among all rows, the largest area is 4, which is the final output for this example. In this example, we have a square matrix where all elements are 1s. The process of pre-computing the heights remains the same. For column 0, each row has a 1, so the heights are 1 for the first row and 2 for the second row, indicating consecutive ones. Similarly, for column 1, the heights are also 1, 2. This gives us the resulting heights matrix, where both rows have heights 1, 1 in the first row and 2, 2 in the second row. Pre-computing these heights lays the foundation for determining the maximum area in the next step. The maximum area calculation begins by sorting the heights for each row in descending order. For row 0, the sorted heights are 1, 1. Calculating the area for each column, we find that column 0 has an area of 1 times open parenthesis 0 plus 1 close parenthesis is equal to 1, and column 1 has an area of 1 times open parenthesis 1 plus 1 close parenthesis is equal to 2, making the maximum area for row 0 equal to 2. For row 1, the sorted heights are 2, 2. Column 0 has an area of 2 times open parenthesis 0 plus 1 close parenthesis is equal to 2, and column 1 has an area of 2 times open parenthesis 1 plus 1 close parenthesis is equal to 4, resulting in a maximum area of 4 for this row. Among all rows, the largest area is 4. This is the final output for this example. Next, we look at a more complex case where the matrix has mixed heights. Here, the input matrix has mixed heights, and the first step is to pre-compute the heights of consecutive ones for each column. For column 0, the first row has a height of 1, the second row increases to 2, and the third row resets to 0 because of a 0 in the matrix. For column 1, the first row has a height of 0, the second row starts at 1, and the third row increases to 2. Finally, for column 2, the heights are 1, 2, and 3 for the 3 rows respectively. This gives us the resulting heights matrix, where each cell represents the height of consecutive ones in that column. Using this matrix, we can now calculate the maximum area row by row. For row 0, the sorted heights are 1, 1, 0. The areas for the columns are 1, 2, and 0 respectively, with the maximum area for this row being 2. For row 1, the sorted heights are 2, 2, 1. The area calculations give 2 for column 0, 4 for column 1, and 3 for column 2, resulting in a maximum area of 4 for this row. Moving to row 2, the sorted heights are 3, 2, 0. Calculating the area, column 0 has an area of 3, column 1 has 4, and column 2 has 0, with the maximum area for this row also being 4. After evaluating all rows, the largest area found across the entire matrix is 4, which becomes our final output for this example. To analyze the time complexity of our algorithm, we can break it into 2 main steps. The first step involves pre-computing the heights for each column in the input matrix. This is done by iterating through each cell of the matrix and calculating the height based on the value above it. Since this involves a single pass through the matrix and each operation is O(1), the time complexity of this step is O rows asterisk cols, where rows represents the number of rows and cols represents the number of columns in the matrix. The second step is sorting and calculating the maximum area for each row. Here, for each row in the heights array, we sort the row, which takes O, cols asterisk log, cols, and then iterate through the sorted row to compute the maximum area, which takes O, cols. Since we repeat these operations for all rows, the time complexity of this step becomes O, rows asterisk, cols asterisk log, cols, plus cols, which simplifies to O, rows asterisk cols asterisk log, cols. Now, to determine the overall time complexity of the algorithm, we combine the time complexities of the 2 steps. The first step, pre-computing the heights, requires O, rows asterisk cols. The second step, sorting and calculating the maximum area, requires O, rows asterisk cols asterisk log, cols. Since O, rows asterisk cols asterisk log, cols, dominates O, rows asterisk cols, the overall time complexity of the entire algorithm is O, rows asterisk cols asterisk log, cols. This is the term that defines the efficiency of our solution, as it captures the most computationally expensive operations. Next, let's analyze the space complexity of the algorithm. The primary space requirement comes from the heights array, which is a 2D list of the same dimensions as the input matrix. This requires O, rows asterisk cols, space. Additionally, during the sorting step, the sorting algorithm may use some temporary storage, but this is generally negligible compared to the space used by the heights array. Other variables, such as the maximum area we track, the sorted row for each iteration, and loop iterators, require only O(1) space. Therefore, when we combine these factors, the overall space complexity of the algorithm is dominated by the heights array, leading to a total space complexity of O, rows asterisk cols. To better understand the efficiency of this approach, let's compare it with a brute force solution. In a naive approach, we would iterate over all possible submatrices of the input matrix, check if each submatrix contains only ones, and calculate its area. Since there are O, rows asterisk cols, caret 2, possible submatrices and verifying each submatrix takes O, rows asterisk cols, operations in the worst case, the time complexity of the brute force approach would be O, rows asterisk cols, caret 3. In contrast, the optimized algorithm drastically improves this by reducing the problem to a row-wise computation of heights, followed by sorting and efficient area calculation for each row. This reduces the time complexity to O, rows asterisk cols asterisk log, cols, which is significantly more efficient and makes the solution practical even for larger input matrices. Finally, let's consider the best, worst, and average case analysis. In the best case, if all elements of the matrix are 0, the heights remain 0, but the algorithm still performs the sorting and area computation steps, resulting in a time complexity of O, rows asterisk cols asterisk log, cols. In the worst case, where all elements are 1, the algorithm performs the full computation of heights and maximum area, but the time complexity remains O, rows asterisk cols asterisk log, cols. Similarly, in the average case, the most computationally expensive operation is still the sorting step, so the time complexity remains dominated by O, rows asterisk cols asterisk log, cols. Mathematically, this is because sorting each row contributes O, rows asterisk cols asterisk log, cols, and pre-computing the heights adds O, rows asterisk cols. Since O, rows asterisk cols asterisk log, cols, is the dominant term, the overall time complexity is O, rows asterisk cols asterisk log, cols, regardless of the input distribution. When solving this problem, there are several common mistakes to watch out for. First, one of the biggest errors is neglecting to sort the column heights after building them. Sorting in descending order is critical because it allows you to maximize the width of the submatrix for each possible height. Without sorting, you might miscalculate the largest area. Another frequent issue is confusion between row and column operations. Remember, the problem only permits rearranging columns within their respective rows, so attempting to rearrange rows violates the constraints. Inefficiency in sorting can also become a problem. Sorting column heights for every row without optimization leads to unnecessary overhead. Instead, aim to use an efficient sorting strategy or cumulative heights to reduce redundant work. Additionally, it's easy to make mistakes in the area calculation by forgetting to multiply the height by the corresponding width. Always double-check that you're applying the correct formula, height asterisk width. Finally, edge cases need special attention. For example, matrices filled entirely with zeros or matrices with just a single row or column can cause runtime errors or incorrect results if not handled properly. Being thorough with these details can make a big difference in solving the problem effectively. Now, let's discuss some key insights that can help you excel in an interview scenario with this problem. First, this problem is essentially a blend of histogram-based area calculations and sorting, so a strong understanding of both techniques is crucial. Interviewers often want to see if you can combine these ideas seamlessly in your approach. Next, optimizing the sorting step is vital since it's typically the most time-consuming operation. Implementing sorting efficiently can significantly improve the performance of your solution. It's also important to clearly explain your approach during an interview. Be prepared to discuss why sorting is necessary and how rearranging columns impacts the result. This demonstrates a deeper understanding of the problem. Additionally, interviewers might introduce variations to test your adaptability, for instance, limiting the number of column swaps or dynamically modifying the matrix dimensions. Being ready for these kinds of follow-up challenges can set you apart as a candidate. This problem also connects to several related problems, which are worth reviewing to deepen your understanding. For example, LeetCode 84, largest rectangle in histogram, forms the foundation for calculating submatrix areas. If you're comfortable with solving the histogram problem, you'll have a much easier time here. Similarly, LeetCode 85, maximal rectangle, is another relevant problem, but it focuses on finding the largest rectangle of ones in a binary matrix without allowing column rearrangements. Another related problem is LeetCode 221, maximal square, which is a simpler variation that involves finding the largest square of ones in a binary matrix. Finally, LeetCode 363, max sum of rectangle no larger than k, tackles a different optimization challenge but shares the matrix-based structure. Exploring these problems can strengthen your problem-solving skills and help you identify patterns that apply across multiple scenarios. Finally, let's explore some alternative approaches and their trade-offs. A brute force approach involves calculating the areas of all possible submatrices. While it's straightforward to implement, it's highly inefficient, with a time complexity of n cubed *m, where n is the number of rows and m is the number of columns. This makes it impractical for larger inputs due to its exponential growth. A more efficient method is the optimized sorting approach, where you build cumulative column heights, sort them in descending order for each row, and calculate the maximum area row by row. This approach has a time complexity of n*m*log m, where sorting dominates the runtime. While it's much more practical, it does require careful implementation to ensure the sorting logic is correct. Another option is a greedy column rearrangement strategy, where you attempt to maximize the height-to-width ratio without explicitly sorting. Although this approach can be faster in certain cases, it doesn't always guarantee the optimal solution, so it's best suited for specific constraints. Understanding these trade-offs can help you choose the right approach based on the problem's requirements. Great job! Today, we learned how to solve the largest submatrix with rearrangements problem using sorting and optimization techniques. Remember to practice similar problems to strengthen your skills. Subscribe for more tutorials, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!